All right, good afternoon. Welcome back. It's a pleasure to introduce Amritanshu Prasad from IMSc, and he will tell us about subgroups of finite abelian groups.
Okay, so I'm going to write integer partition as either it's just a sequence of weakly decreasing sequence of positive integers, and there's another way to write it which is called the exponential notation. So what this means is that 1 appears in this sequence L1 times, 2 appears L2 times, 3 appears L3 times, and so on. So sometimes it's convenient to write it like this, and sometimes it's convenient to write it like this. So for example, if I take 5, 3, 3, 1, I would write this as 1 to the 1, 2 to the power 0, which you can probably drop, 3 to the power 2, 5 to the power 1. And so a finite abelian group, we'll just focus on P groups. I'll use this notation AP lambda. This is just you take integers mod P to the I Li times. Right? Another way of thinking about it is it's Z P to the power lambda 1 plus okay, this is just the cyclic group of order P to the lambda. And so the question that we'll start off by asking, which a priori doesn't seem to have much to do with subgroups, but suppose I define G lambda P to be the automorphism group of AP lambda. So this is aut of AP lambda. So you can ask yourself, what are the orbits for the action of the automorphism group on this finite abelian? So for example, if you just take lambda to be 1, 1, 1, 1, 1, then you're looking at an elementary abelian P group, or just a vector space over the field with P elements. And then there are only two kinds of elements really. There are non-zero elements. You can map any non-zero element to any other non-zero element. And there's zero. But in general, there's several orbits, and we're just going to see how to think about them. And then we'll see how it's related to counting subgroups of finite abelian groups. So, so let's look at maybe the next simplest example. So if you look at the cyclic group of order P to the power k, then here the number of orbits there are actually how many? K plus 1. So if k is 1, then there's 0 and non-zero. Yeah, so. And what are these orbits? Well, they're represented by 1, P, P to the k minus 1, and P to the k, which is equal to 0. So, so these, they're just k plus 1 orbits. And yeah, so given A in Zp to the k, I'll say that Vpa is I if A is in the same orbit as P to the power I. Okay, so that's just the p-adic valuation, so to speak. Okay, so to move towards automorphisms, here's a very simple observation. So suppose I have A in integers mod P to the k, and B in integers mod P to the S, I'll ask a simple question. Does there exist a homomorphism phi from Z mod P to the K to Z mod P to the S such that phi of A is equal to B? So that's the question, and this answer will depend on these p-adic valuations. So let's suppose that the valuation, I'm not supposed to write here, is it? So VPA is I and VPB is, what do I call it? Is J. So this is not difficult to figure out. One thing is that if a homomorphism takes A to B, then certainly J should be, so this A is P to the I times something, so B should also be P to the I times something. So certainly what we must have is that J is greater than or equal to I. And then if you look at the order of P to the I, it's K minus I. And that order should be greater than or equal to the order of B. So we should also have the second condition that K minus I is greater than or equal to S minus J. So this is actually easy to see that this is an if and only if condition. So we have these sort of conditions, and intuitively what you should think of is that if there is a homomorphism which takes A to B, then somehow B is more degenerate than A. So the most degenerate thing in an abelian group is 0. And so we want to somehow think of this as giving rise to a partial order. So let's just formalize that. So I call this the fundamental poset. P, and as a set, it's just the set of pairs I comma k. K is this Z mod P to the K, so K can be anything greater than or equal to 1. And I is the valuation, so it can be anything between 0, P to the power 0 and K. But I will stop at K. I will just, that's the 0 element, so I'll leave it out. And we'll use this to define a partial order on P. Okay, so let's just draw the Hasse diagram of this partially ordered set. So, so you have this element 0, 1. This represents a non-zero element of Z mod PZ. And when you look at Z mod P squared Z, you have 0, 2 and 1, 2. When you look at Z mod P cubed, you have 0, 3, 1, 3, 2, 3. And it goes on, right? And the cover relations are just these things. I hope I drew them all. Okay, so this is the Hasse diagram of P. And from this you can easily visualize all these elements in finite abelian groups, in cyclic groups, and see how they, they can map to each other. Now, we will use this to, in fact, address the original problem where we look at a more general group. So, So the idea here is to associate to each element of an abelian group a certain ideal inside this poset. So if P is a poset, an ideal I is a subset such that if X belongs to Y, Y is less than or equal to X implies that Y belongs to Y. So this is the definition of ideal. Right, so if I take some element here, I can look at the ideal generated by it, which means the smallest ideal that contains that element. So if I were to take this element, if this is in an ideal, everything that is less than or equal to it would be in the ideal. So all these things below 2 to the 5, 1 to the 1, 3 and 1, 2, all this stuff should be in the ideal. I could take a multiple elements and look at the ideal generated by them. It's the smallest ideal that contains all those elements. So, so now here's the construction. So suppose I'm given A is A1, A2, AL in AP lambda. And this means that I'm looking at this model of lambda and this model of AP lambda. These are the cyclic paths. So this AI is in Z mod P to the lambda. And to each of these elements, I can associate a point in this set. So let me, for example, take A to be just so I'm going to P is some prime, and I could this I might have an element like 2p squared or something where when p is greater than 2, but just by scaling it by an appropriate unit, you can just make it a power of p. And as far as studying orbits is concerned, it doesn't really matter. So you can just replace each coordinate by a power of p. So I'll only be looking at elements which are powers of p. It's only the power that matters. So here's an element. So this p cubed is in, I should say something about lambda. So my lambda is the same thing, 5331. So what that means is that this is p squared in z mod p to the 5z. This is p cubed in z mod p cubed z. This is p in z mod p cubed z. And this is 1 in z mod p. And now to this element, so to each of these elements, I will associate a point in this fundamental poset. So this is p squared inside z mod p to the 5. So I'm going to put this point. So this corresponds to p squared inside z mod p to the 5. And now from this coordinate of that group, I can get all these elements in various cyclic groups and maybe elements in other coordinates of that group. Now this is p cubed in, so this point doesn't really live in my poset, so I'm just going to ignore it. This is 0 really. If it were p squared, for example, then I would put it down here. But it's p cubed, I'll just ignore it completely. And this is p also in p cubed, right? Remember, there's another copy of z mod p cubed z. So that's p, so that's over here. And then there's 1, which is over here. So looks like I've ended up picking these 3 elements from my thing. And then I just create an order ideal from it. So the smallest ideal containing these elements is everything that, so this guy has to be in it, right? This guy has to be in it, and all these numbers below. So everything sort of below this orange line, this is my order ideal. Right? And well, this is an infinite poset, so this sort of goes on. So this is I'll call this the boundary of the ideal I. So IA is equal to the ideal generated by the set VP AI comma lambda I goes from 1 to L, where I assume that AI not equal to 0. So what I'm doing now is to each element in the group, I have associated an ideal in the fundamental poset. Now this ideal is going to be generated by elements in the columns. So you can think of this poset as having columns. The first column corresponds to Z mod PZ, the second column, well, from the right corresponds to Z mod P squared, and so on. And so you can think of each column as corresponding to Z mod P the I, but this ideal is going to be generated by the columns which actually occur in the group. So, so we'll say that I is generated by lambda if, okay, so another thing about ideals is that ideals are determined by their maximal elements. So each ideal is the smallest ideal contained in its maximal elements. And these maximal elements, they form what are called anti-chains. Subsets where no two elements are comparable. So ideals are in bijection with anti-chains. So I is generated by lambda if max I, every point I comma k in max I, k is actually a part of lambda. Or maybe I could say Lk is positive. K occurs in lambda. Now I've switched to this exponential notation. So this is our definition. Maybe I should say generated in lambda, not by lambda. Okay. So I mean, I'm not saying that each lambda generates one ideal. I'm just saying that the ideal is generated by elements in the columns corresponding to lambda. So I is generated in lambda. So what you get now is a map I from AP lambda to the set of ideals of P that are generated in lambda. So this is the set of ideals in P generated in lambda. And it's not difficult to show that suppose I have A in AP lambda, B in AP mu, so these are now two different partitions, then so what we'll do is we'll generalize this this result here. Like we asked if I have two different elements in cyclic groups, right? When is one the image, a homomorphic image of the other? We can generalize it to any finite abelian group. There exists phi, a homomorphism, well, let's just write it like this, AP lambda to AP mu, a group homomorphism such that phi of A is equal to B if and only if. So what should you expect? The element B, the ideal of B should be smaller than the ideal of A, right? The ideal of A is telling you what all you can reach through homomorphisms from A. So B should be reachable. So the ideal of B should be contained in the ideal of A. So So that's quite easy to show, and there's actually a slightly stronger statement that you can make, which can call a theorem. So this it's quite easy actually, but it was one of the results. It's the way of doing it that makes it interesting. So this is my first paper in combinatorics, by the way. So what's the theorem? So yeah, so A and B lie in the same G lambda orbit, G P lambda orbit. That is, there's an automorphism that takes A to B if and only if IA is equal to IB. Okay, so what we're saying is that this map gives rise to a bijection from G lambda P mod A lambda P to J lambda P. And in fact, it's a bijection that respects degeneration. So if an ideal here is contained in an ideal there, then those orbits degenerate to each other. Right. So so here's a very interesting point. So if this element were 0, then I would have nothing. IA would be the empty ideal because there would be nothing in this set, right? We are only looking at the non-zero coordinates. So the empty ideal corresponds to the 0 orbit, and in this case, for the group 5331, we are just looking at 3 columns here. So so there's the column corresponding to 5. There's the column corresponding to 3, and there's the column corresponding to 1. So if you want to list all the orbits, you just have to find all the ideals in the fundamental post set that are generated by these 3 columns, which means you have to find anti-chains in the fundamental post set that are contained in these columns. Right, so the orbits are in bijection with anti-chains in these post sets that are contained in these columns. Okay, so how do we? I'll just indicate the proof of this. It's not very difficult. One way to do it is anyway. This is a useful notion. So given an ideal, you can talk about its boundary, as I hinted here. So, so I'll say R, or maybe think of it as a vector. It will have one coordinate for each coordinate in the group. R1, R2, RL, where Ri is the, maybe Rj is the least integer I, such that I comma lambda j belongs to, so this is associated to R of I. So let's say, so in this case the boundary is given by 2, 1, 1, 0, right? So in our running example, so this lets us count so if I want to count the number of orbits, I just have to count the number of such vectors. So let's just think about what that means. So if you're looking at the boundary of an ideal, one thing you note is that suppose this element is there, then where can the boundary be at the next stage? So it could go down or it could go up. It couldn't be like up here, because if it were up here, then this element would also be in the ideal. It couldn't be further down here, because if it were further down here, then this element would also be in the ideal. So the boundary is sort of a curve which, either goes down one step or up one step, not anymore. So its slope has to be either +1 or -1 at each stage. And it cannot even be flat between two consecutive rows, because they are sort of staggered. But of course, if you only focus on these columns, then in this case, for example, these three elements on the boundary are parallel. So you may see, yeah. Okay, so what that's saying is that R is a boundary of an ideal generated in lambda if and only if actually I probably don't even need this condition. If and only if so the inequalities are Ri is less than or equal to Ri minus 1 is less than or equal to Ri plus lambda I minus 1 minus lambda I. So these are the extreme cases. So if you're starting from Ri minus 1, then so you're starting from some point here in the fundamental poset, and say you're jumping to this column here, then either this this valuation 1 remains constant. That's the lowest possible value. So Ri has to be less than or equal to. Oh yeah, but we are going from larger to smaller. So okay, so we are starting off say somewhere here and we're looking here. So then the lowest possible will be Ri itself, and the highest possible, well, the slope has to be 1, so it has to be this other angle. So these are the two extremes. So if you start with Ri minus 1 comma lambda I, then if you go lambda I minus 1, then if you go up or you go down, so if you go up, then you'll end up with I think this guy. If you go down, you'll end up with Ri. So these are the two extremes, and everything must lie in between. And and to get this process started, well, you can start off with RL. Well, RL can be anything between 0 and lambda L. So now we can easily write down the number of orbits. So what is this? So firstly, I have lambda L plus 1 choices for RL. Lambda L plus 1. And then I have product I goes from 1 to L minus 1. And what is the number of choices I have? So having fixed RL, the number of choices for the next thing is R I plus 1 or should it be lambda I? Okay. Yeah, I think this is correct. So you can get a formula for the number of orbits. And what's interesting here is that this number does not even depend on P, right? So it's completely independent of P. Lambdas are decreasing. Okay, so that's the problem, yeah. So I should write it like, So in this example, let's just do this example. So how many orbits do we have here? So 6 into, and so that's the first thing. Oh, yeah, I keep getting lambda L. Okay, yeah, we're starting with the last one. So it's 1 plus 1, that's 2. So A 5 3 3 1 mod G P 5 3 3 1 is 2 into, okay, and then the next thing is we just take the difference between the successive things. The next one is 3. So 3 minus 1 plus 1, which is 3. Then the next is 3 minus 3 plus 1, which is 1. And then there's 5 minus, and so there's totally 12 orbits. Huh? Okay, so that is the hardest part of this, by the way. So yeah, is multiplying the numbers, right? I mean, the rest is really simple. So yeah. Okay, so let's just look at this again, and I'm going to draw a few pictures. So I think Christopher already mentioned this, that if you have a partition, then it's nice to visualize it using a Young diagram. So 5, 3, 3, 1, and so this is the Young diagram of 5, 3, 3, 1. So there, you see there are 5 boxes, 3 boxes, 3 boxes, 1 box, and okay, so given 2 Young diagrams, we'll say that lambda contains mu if the Young diagram, so given 2 partitions, we'll say lambda contains mu if the Young diagram of lambda contains the Young diagram of mu, which means every box of this Young diagram is a box of this Young diagram, right? Which also means that the ith part of mu, if you write it in the first convention, is less than or equal to the ith part of lambda for every lambda. So yeah, and we'll say that lambda, okay, so so we'll say that lambda minus mu is a horizontal strip if it contains no more than one box in each column. These boxes are actually, I think you should call them cells, but anyway, each column. So for example, we could, so in this case, okay, so what I want to say is that given this number, you may have seen it if you're trying to compute the number of partitions mu such that lambda minus mu is a horizontal strip. What it is so you can compute it from R as follows. So mu L equals RL, mu I equals lambda I plus 1 plus Ri minus Ri. So in this case, R is 2110. So so this is a 0. So we remove this box. Mu 2 is 1 plus 1 plus 1. So that's 2. Mu 3 is 3 plus 0, I guess. 2, 1, 1, 0, and then this is 3 plus 1, 4. So the shaded boxes are the partition mu. The total thing is the partition lambda. And you can recover r's from mu's by just reversing these equations. So what we are saying is that this so the number of is equal to the number of partitions mu such that lambda minus mu is a horizontal strip. And this bijection is given by so this is j lambda p, and so there's actually a bijection like this, and it's given by these equations here. So what is actually happening, as we shall see in a moment, is that if you have an element A in A, then you can look at the subgroup generated by A. So just the cyclic group generated by A, and this AP lambda by ZA will be isomorphic to ZP mu, where mu is obtained from lambda by this kind of correspondence. Okay, so we'll come to that in a minute, but I just want to pause for a minute here and make a few remarks. So one thing that we noticed here is that a corollary of this result, which is it, this bijection is worth noticing, is that so if we have two elements A in AB in the same group AP lambda, and they exist phi1 and phi2 automorphisms of AP lambda, not automorphisms, endomorphisms, such that phi1 of A is equal to B and phi2 of B is equal to A, then A and B are actually in the same orbit. They exist phi in aught AP lambda such that phi of A is equal to AP mu. Thanks. This comes really innocuously out of that, but it's an interesting statement. If one element in a group is an endomorphic image of another, and vice versa, if two elements in a group are endomorphic images of each other, then they must be automorphic images. So this one is fairly easy to prove in this case, but there's theorem that I proved a little later. So with Wesley Calvert and Kudal Datta, and it says that this holds also not just for elements but also for subgroups. If A and B are subgroups of AP lambda, and phi, the same statement, right? They exist phi1, phi2 in end AP lambda such that phi1 of A is equal to B, phi2 of B is equal to A, then there exists phi in aught AP lambda such that phi of A is equal to B. And this actually uses a proof of Mackey and Kaplansky, a theorem on the classification of a certain family of infinite, countably infinite abelian groups. So it's called Ulm's theorem. I haven't thought about this for many years, but I kind of wonder, like, what are the groups for which you can do things like this and like this. Another interesting point that probably hasn't been looked at too much, unless so what we have looked at is we have looked at AP lambda mod GP lambda, but we could also look at AP lambda to the power k, a kth power of AP lambda mod GP lambda, and try to understand this. Okay, there's a similar theorem for pairs. So what I'm saying is that, G acts on AB by GA GB, the diagonal action. And you want to understand the number of orbits of this. So you could ask, what is this, right? So there's a similar theorem for pairs. In fact, this theorem for subgroups we prove using the theorem for n tuples. So I mean, okay, k tuples, right? So A1. Now these are not coordinates, so these are actually elements of the group. Maybe I'll call them G1 up to GK. What should I call them? Okay, I'll just call them A1 up to AK, but remember now these are in the whole group. And a very strange thing seems to be happening, which is, okay, so this was in the PhD thesis of Anil, that if you look at this number, then this is given by a polynomial in P. And for k equals 2, this was proved in Anil's PhD thesis, and later Anil proved that this polynomial has non-negative integer coefficients for k equals 2, which is quite, I mean, surprising result. But for larger k, I believe this is still worth exploring. So is this, so conjecture, there exists a polynomial with non-negative integer coefficients. So maybe f lambda, if you know what this means, such that so that's something to think about during the coffee break. Is it time? This thing is saying, oh, okay, 46 minutes. Okay, so I still have 4 minutes. Okay, good.
The top equation, the size of the number of orbits is f sub lambda of p, and then there's a conjecture. What is known at the top, and what is the conjecture?
Okay.
Okay.
The conjecture is here. This was just,
but
yeah.
It's known for k equals 2.
For k equals 2, it's known. Yeah. For k greater than 2, I don't think we even know that a polynomial exists.
Okay, so it's sort of 2.
Yeah,
yeah.
Yeah. So one of the big challenges of working with these finite abelian groups is that we don't understand this automorphism group that well in some ways. So let me explain what it means to not understand. We understand in the sense we know the order of the group. We can easily write down matrices which represent elements of the group and so on. But there's some very nice things about, but to explain what we don't know, let me tell you what an easy solution to this could be. So this would just be by Burnside's lemma, right? And if you could just write down how many fixed points there are. So what should I call it? Fixed points of G on AP lambda to the power K. So if you could just write down how many elements of G there are with a given number of fixed points, then you would be able to, in a way that is sort of P independent and combinatorial, then you would be able to solve this easily. That's true. So, yeah, but this formula has P in the sum, already in this sum. So somehow, you know, the number of terms in this already depends on P. So, yeah. I didn't write it inside because this somehow seems simpler than that, because there it seems like you'll have to take a different set each time and figure out the number of fixed points. I'm saying you just have to solve one problem, which is figure out the number of fixed points on AP lambda itself, not on some power of AP. But of course, it's a triviality because fixed points on AP lambda to the power K are K tuples of fixed points. So there's nothing. Okay, so let me just show you another problem which has similar similar nature. So suppose I want to look at matrices, say Mn Fq squared. Now GLN Fq acts on these pairs, right? By conjugation, simultaneous conjugation. And you could ask for the number of conjugacy classes on pairs. So this is the sort of classical matrix pair problem, but it's a combinatorial version. You work over finite fields, and you don't ask for a theory of these things. I think you just ask for the number. And this is actually a tractable problem. I can write 3 or 4 lines of code on my computer and get this for any n. Well, given some amount of computational time, but no, as a formal polynomial in Q. But it also falls under the ambit of what's called Katz's conjecture. So after all, what this is you look at the quiver with one vertex and 2 arcs, and you ask what are the isomorphism classes of modules for this quiver, or what are the isomorphism classes of modules for the free algebra on 2 generators. Over finite fields, Katz's conjectured that for any quiver whatsoever, this count is a polynomial in Q with non-negative integer coefficients. And that you can't prove Katz's conjecture using this Burnside's lemma technique, but you can certainly compute these things for each n using Burnside's lemma, because we have a pretty good understanding of matrices over GLN FQ. If I tell you that, if you give me the order of a centralizer, I can tell you exactly how many matrices are there with that centralizer order. So I can give you a list of centralizer class sizes and the frequencies with which they occur using the Jordan canonical form for finite fields. So is that the time left, or is that the time that's... It was saying 55 minutes earlier, so I thought it was overtime. Now
The schedule says that you have an hour and a half. I don't know who.
oh, okay. So, but maybe I should stop at some point, right? Yeah, okay, so I've been following that, but it's been saying random. It's counting down, I know.
Yes.
Yeah.
Counting down.
Okay.
But
Okay.
you have time.
How much time do I have?
The schedule says you have an hour and a half. I don't know who wrote the schedule.
An hour and a half? I don't need an hour and a half. No, we have, huh? Okay. Tutorial, yeah, it's time for the tutorial. So I was supposed to stop at 3:20 if I started at 2:30. So yeah. So yeah.
K equal to 2 is the polynomial coefficient. Do they count something?
Yes, they have special meanings when evaluated at 1, -1 and 0. And I believe that actually the coefficients also have some nicer combinatorial interpretation. I'm able to get some results when the partitions parts are all distinct. But when they are not distinct, it is still slightly unclear.
Yeah, but we really have to have the tutorial, yeah.
I mean, is this conjecture completely open or is it no?
As far as I know, it's open.
K equal to 2,
It's
the positivity part was a bit difficult in the beginning, which got solved, but the polynomial part got solved long before when I was working with.
that was his PhD thesis, but he never used this result, which I feel that could have been. You never used this, right? Yeah. Yeah.
Do you have a conjecture about the degree of these polynomials?
I think so. Yeah, that we can figure out the degree of these polynomials.
Degree of the
Yeah.
polynomial is lambda 1, the highest part. Yes.
And Katz's conjecture is completely open or?
No, it's proved. It's a theorem of Hausel, Letellier, and Hunnell's paper from a few years ago. It uses like all this Étale cohomology, Deline's theorem.
Yeah, there must be some cohomological proof.
Yeah. Huh? Ulm's theorem is a theorem for the classification of countable. It's a generalization of the structure theorem for finite abelian groups to countable P torsion. Let's say torsion, countable torsion, and you don't want like these factors like QP mod ZP in them. That has a certain name. So for that class, so there's a lovely book by Kaplansky called Infinite Abelian Groups. It's really like one of those very special books, so which one can look at. So, yeah. Okay, so.